All right, it's 1 o'clock on a Monday. Thank you all for coming today. I appreciate it. On Friday, we talked about infrared spectroscopy or infrared spectrometry. What does infrared tell you about? There's one thing. Functional groups, exactly. So it tells you what is in the molecule in terms of functional groups, but it pretty much doesn't tell you anything else. Mass spectrometry is what we're going to talk about today. Mass spec gives you different information, the primary thing being the mass of the molecule. So we'll get into some little details that it tells you. There's a few things that we can figure out by looking at it, and a few things that we can deduce after knowing that previous stuff. But the number one thing is the mass of the molecule. Just like on Friday, my primary interest in this class is not that you know exactly how the instrument works, but be able to interpret the data that it gives you and turn those data into information about the molecule. So I'm going to spend about 5 to 10 minutes giving you a little bit of a background on how a mass spec works. There have been many developments, and this is going to be dramatically oversimplified and more historical than anything else. So don't assume that in the next 5 minutes you're going to know everything about the inner workings of a mass spec, but I want to give you just a general overview because I think understanding is worthwhile. But you can write any of this stuff down. You don't really have to because our goal is going to be interpreting. So we're going to start in about 10 minutes looking at spectra and interpreting them. That's where you need to write stuff down. That's what I'll be asking you about. So we'll start going forward. That is to say, here's the molecule. Here's what the mass spec looks like. But your quizzes, which is the overall goal of spectroscopy, is to have a spectra and be able to say, what does this mean? So basically kind of doing it backwards. We'll be doing that in class today. We'll be doing it in lab starting today. We'll be running IRs starting today. The out of lab assignment for week 2 and 3, which is today and next week, is to work through a set of problems that are about lab and IR mass spec. Those aren't due until next Friday. But I highly recommend that you guys work on those today or tomorrow because your quiz on mass spec is on Wednesday and IR is on Wednesday. So the best way to learn this stuff is to practice it. So just, I don't know if you have a textbook or not. If you have one, there's lots of questions in there. The internet has lots of questions, but a textbook is a good place to find them. Obviously, there's a lot of problems on the Canvas site. Kind of the more mass specs you can find and look at and interpret. They get repetitive, and I don't love flashcards, so my preferred way to do it is to look at a bunch of specs, but whatever works for you guys is okay. All right, so that being said, here's our background to mass spec. That's a molecule. It's 3 carbons in a row. It's an alkane. What's its name? It's not methane. It's not ethane. Propane. Propane. Perfect. All right, so propane is your three carbon chunk. There's not much to propane. It's just this little guy. We're going to have to do some math in mass spec. You can use a calculator on your quiz on Wednesday if you need to. But propane, it's 3 carbons. Carbon weighs 12. 12 times 3 is 36. And there are 8 hydrogens, which weighs 8. So this molecule weighs what? 36 plus 8. Oh, we're starting off early. 44. Correct. Good job. It weighs 44. All right, we can all do this math. You don't need to be able to do this in your head. I know you could on a piece of paper, but I'm going to start calling on you guys soon because I know all your names, so good news. So this molecule weighs 44. So the principal piece of information we're going to get out of a mass spec is what this molecule weighs. So in general, again, this is very, very, very surface level how things work. What we do in a mass spec is we bombard our molecule with high energy electrons. What electrons would like more than anything else is to be paired up. And so a high energy electron, if you are shooting it at a sample, what it is going to do is to try to pull an electron out of your molecule. So thinking about where electrons are in a molecule like propane, electrons exist in core electrons, right, that are very close to the center of the nucleus. They're in valence electrons, and the valence electrons exist in 2 different places. They could either be part of bonds or part of lone pairs. So in propane, we don't have any lone pairs. So all of our electrons either exist in the core, which are pretty close to the nucleus and pretty inaccessible, or they're in bonds. That make sense? Okay, so where do you think you're more likely to remove an electron from a molecule? Those core electrons that are stuck in the middle, or the bonds that are around the outside? yeah, the bond's right around the outside. So in this molecule, there's a couple different places where bonds exist. There's bonds between carbons and hydrogens, and there's bonds between carbons and carbons. And all of those bonds have 2 electrons. And so this high energy electron that the mass spec is using to basically bombard your molecules and try to pull an electron out will either pull 0 electrons out or it might pull 1 electron. There's a lot of probability and statistics in this, not that you need to know how all of that works, but basically you're injecting a bunch of sample and you're shooting it with a bunch of electrons and kind of hoping for the best. And for some of your molecules, what you'll do is pull an electron out. So that electron is going to take one and they're going to run away in a pair of electrons. And it'll leave your molecule with 1 fewer electron than it started with. So you're right, bonds are the most likely place by far that you're going to lose an electron. If you lose an electron from a carbon-hydrogen bond, then your bond wouldn't have 2 electrons anymore, it would just have 1. Make sense? And for our purposes, it wouldn't really matter which of those carbon-hydrogen bonds was reduced down to 2 electrons. But one of those bonds could then have just 1 electron instead. So let's say that we did it right here. We pulled an electron out of that bond. What you would get out would be some propane that would have the same number of carbons, and it would actually have the same number of hydrogens. It would only be down 1 electron. And it turns out that 1 electron is sufficient to act as a bond and hold together a carbon and a hydrogen. So what's different about this thing right here? It's only lost 1 electron. Is the mass the same? Take a wild guess. Worst case, you're wrong. So technically, the mass would be different because electrons do have mass. But remember that going back to really early Gen Chem 1, the mass of an electron is so small compared to a neutron or a proton that for all intensive purposes, it's practically 0. So when we said that propane weighed 44, we were just counting the neutrons and the protons. So technically, yes, the mass changes, but practically, no, right? If you lost a hair, you would still weigh the same amount. Not really, but practically. So losing an electron, they weigh the same amount. So the mass of this thing is still going to be 44. But you have lost an electron, and this is important. If you lose an electron, the charge changes. So what's the charge of the molecule when you remove a negative? Savannah, go. Take away a negative, what do you get? Right. So what's the charge of the molecule now? Yep. So this molecule is the same, except that it now has a net positive charge. That's it. So that's our purpose. When we shoot this molecule with an electron, is that we then get a positive charge. Yes, ma'am.
Why is it that when are you shooting 2 electrons or are you taking 2 electrons out?
You're basically just shooting it with 1 electron at a time, but
Okay.
electrons like to pair up. So that 1 electron that it gets shot with, if it strikes this molecule, what it attempts to do is take an electron away. Think of an electron like an electrophile, like it would love another electron. So basically it just rips an electron out of the molecule. They run away as a happy couple of 2 electrons. And so basically that's how we take an electron away. It seems counterintuitive that you shoot it with an electron to remove an electron, but that's how it works. They basically run away with it. So what we would get is a molecule that has an ion. So we're going to start referring this as now and going forward as this is our molecular ion. Or we shorthand it as big M with a little plus charge. It's the molecule with just a positive charge. Again, the mass didn't really change. It just has a charge. All right, so what we do now is we pass this thing through a magnet. And as this molecule moves through a magnet, what would happen to the molecular ion as it's moving through there is that it would be affected by the charges on the magnet. So its path would actually be bent, its trajectory would be moved. Because any positive charge that goes near a positive charge will be repelled, Any positive charge that goes near a negative charge would be attracted. So the path of this would veer toward the negative, and you would see it start to do this. It would be bent. And what we will have at the other end of this is a detector. And much like most instruments, we have something that happens or changes with a sample, and then you detect what comes out the other side. All right, and in our detector, we can actually detect where each individual ion strikes the detector. And so if it strikes there, or it strikes there, or it strikes there, we can measure that. And that's practically what's going to come out as in the mass spec is what different ions hit the detector at different places and how many. So thinking of the things that can change how much its path is bent, imagine that I am just rolling random balls down this little aisle between the seats, and Caleb is sitting there blowing on it. If I roll a bowling ball, you're blowing on it, is its path going to change?
No.
Not really, but maybe a little bit, but not really, right? So if it starts getting lighter and lighter and lighter, and I roll a soccer ball, maybe more than a bowling ball, but maybe a little bit, right? We don't have a lot of big, very light. Let's imagine like one of the little kiddie kickballs, right? Remember those? So those, you're feeling strong, you're blowing really hard, you might actually be able to move the trajectory of that, right? If I somehow was able to roll a balloon down there, you'd definitely be able to roll its trajectory. So what's different between all of those? Why is it that you can affect some and not others? Yeah, the mass. So a mass dramatically impacts how much inertia there is, and so how easy or hard it is to change their trajectory. And so the mass of the molecule, or the ion in this case, is going to impact primarily how much that path bends, and therefore where it impacts the detector. And so a larger molecule would have its path bent less by a smaller amount. And so these things up here maybe would have a larger mass, and down here would have a smaller mass. And it is going to be proportional to that. So depending on where it strikes the detector, we can actually measure the mass of our molecule that strikes the detector. That's all just based on how much their path bends going through that magnet. Technically, the charge would also impact it, because if you've got a charge of +2, then it would impact, the path would change twice as much. But with mass spec, we almost, when we're doing this, we almost never see a charge of +2. So it's just going to be a +1 is going to be the charge. So while a charge could impact this, practically we always just see a +1. So what the detector will give you is it's really going to give you a where did it strike this? And where it strikes the detector depends on two things. The first is the mass. Oops. Not writing anymore. There we go. It's going to give you the mass divided by the charge. Those are divided because the mass is something where a larger mass would result in a being farther to the right on this detector, if you were to look at it sideways, and a larger charge would result in it being further to the left. So they're inversely proportional. A large charge makes the path bend more, a large mass makes the path bend less. But because our charge is always going to be +1, we don't really need to worry about the Z part of this. It's just going to be the mass. That's practically what we see. Does that make sense? Whether or not, do you get the idea? So that's my brief intro. All right, before we move on, I do want to tell you there's one other thing that could happen here, which is that you could, again, it's all probability and statistics, it's possible that what you could do is remove an electron from one of those carbon-carbon bonds. And if you remove an electron from a carbon-carbon bond, the molecule breaks, because one electron is sufficient to hold on a hydrogen, but is not sufficient to hold carbons in a larger molecule. So the molecule could break there, and if it breaks there, you would end up with two chunks. One chunk would get that one electron, The other chunk would have a formal positive charge. So if that happened, you would end up with something like this. This is going to be a small part of what we're doing going forward, but I do want to notify it right now while we're looking at this. So again, if you happen to remove an electron from a carbon-carbon bond, you'll end up with two chunks instead of the molecular ion. You break the molecule apart. We don't get to choose. It's all pretty random. You're just shooting electrons at molecules. Electrons are small, molecules are small. You don't know what you're doing. Okay, questions on any of that? All right, so we are going to stop with that. We're going to go to a screen share. All right, so we're going to move over to your spectra that you should have right now. So go ahead and get those out. And that's where we're going to go from for the rest of today. All right. So this is what it would look like when you get that information from the detector. And so these peaks here, all of these peaks are indicating some ion hitting your detector at some different place. These are the ones that have had their path bent more. These are the ones that have had their path bent less. These are the heavier ones that it had less of an impact. These are the smaller ones that had a greater impact. And the mass spec, it's done this enough times that we can exactly say how much each of those ions weighs. So these are actually, it's actually counting specific ions. So it might be saying 8 hit here and 60 hit here, et cetera, et cetera, et cetera. The single most important peak for us is the one that is farthest to the right, the tallest one in that chunk. So you want to look farthest to the right, which would be these guys right here. And the tallest one in that group is going to be your molecular ion or your M+. And that's what we were talking about. That is the molecule with plus charge. That peak shows up right there at 206. And so you can say that the molecule weighs 206 atomic mass units, or grams per mole. That's the mass of the molecule. That is incredibly simple to do. It is also the most important piece of information. Ta-da. There are more things that we can get out of mass spec, but that is always going to be the number one. So you know the mass of this molecule. I gave you the molecule right here. But if you didn't know that this was ibuprofen, you would look at that mass spec and say, I've got a peak of 206, and that's my molecular ion. All right, flashback like 3 minutes. What do you think these smaller mass ions are? Yeah, those are the fragments. So this is what we might call the fragmentation pattern for the molecule. You can try to figure out what those are if you want to. You can look at their mass and try to figure out, if you really love puzzles, where exactly, what chunks of this molecule fell apart to give you that. We are not going to focus on that, and I am never going to ask you to do that. Largely what that can help you do is figure out more about the carbon-hydrogen framework of the molecule, but we're going to do that with NMR, which comes next. NMR is a lot more of a clear way to do that. But you can kind of imagine, mostly what we do with this is treat it like a fingerprint, like the fingerprint region, where if you run a mass spec and you have a database, our mass spec that we have up in the lab has a database to compare it to. Basically, it just scans all the mass specs that have ever been run and says, oh, it looks like this one. This is possibly like matching a fingerprint. But if you don't have any of that stuff and you don't have a database of mass specs in your memory, then you look at this and say the mass is 206, so the molecule weighs 206. How you feeling? Okay, great. So let me give you a little bit more information about this. Let's zoom in. So we can see that there is that peak at 206. I will tell you what those, or write up what those numbers are, since you can't really zoom in on a piece of paper very well. But you can see that this was 200, 202, 204, 206, and that peak is appearing exactly at 206. All right, Caleb, you're probably in the best position to read the periodic table. How much does carbon weigh?
Whoa, no. I just overthought that.
Yeah, you're right. It's not exactly 12 though. What is it?
Oh, 12.01.
12.011. All right, anybody remember why those things have masses that are not nice whole numbers?
Because of electrons.
Close. It's not electrons, it's a different subatomic particle that varies a little bit. It gives you isotopes. Okay.
Neutrons.
Neutrons. Atoms have isotopes, and isotopes come from the fact that carbon is carbon because it has 6 protons. Often it has 6 neutrons, but sometimes it has 7. So neutrons can change without the identity of the element changing. Therefore, atoms have isotopes, which for the most part don't really impact very much for us. Carbon has an average mass of 12.011 because roughly 99% of the time it's carbon 12, but 1% of the time it's carbon 13. And this is true of all the carbons in your body and the carbons you find in rocks. This is how carbon dating works, all of that good stuff. But we see this when we run a mass spec because it's exactly measuring how much a molecule weighs. So ibuprofen weighs 206 if all of the carbons weigh 12. But what would ibuprofen weigh if one of your carbons weighed 13 instead? It's not 206, 207. So what you will see, again, there's a lot of probability here, is that most of the time, all of the carbons in ibuprofen weigh 12. So ibuprofen weighs 206. But sometimes you'll have a carbon 13 in there, and then it would weigh 207. So you will approximately always have a peak 1 higher than your mass, because practically your chances of having a carbon 13, well, it's 1% if you only had 1 carbon. But if you had 2 carbons, or like ibuprofen, I don't remember, but ibuprofen has whatever, 14 carbons, something. We could look at it, but it's more than 1% because you got a bunch of different carbons. Furthermore, hydrogen weighs not exactly 1, it's 1.008 because there's hydrogens that weigh 2. And so you have, if your molecule has carbon or hydrogen, and it's organic chemistry, so every molecule has carbon and hydrogen, you're gonna have what we call an M+1 here, which is not a very fancy term, but it's just the mass that's 1 higher. And where does that come from? Yeah, just isotopes. And for carbon and hydrogen, the isotopes are pretty predictable. You'll get a little bit of +1. You shouldn't worry too much about that. It's gonna be there. It doesn't impact anything, but that's gonna end up being something important for later on today. So you'll see an M+1 peak. Don't worry about it. It means you have carbon or hydrogen, which isn't very helpful for us because obviously you have carbon or hydrogen. All right, so that's ibuprofen. Sound good? Right? All of these other things here are fragments, and I'm not too worried about which one's taller or shorter. The taller kind of means that you're more likely to break a carbon-carbon bond to give you this than you are to break a carbon-hydrogen bond and give you this. But that doesn't really impact the fact that this one is your molecular ion. Hopefully this is pretty intuitive, but the reason that the molecular ion is the one farthest to the right is because this is the one with the greatest mass. And if a molecule breaks into smaller pieces, it only gets smaller. So that's why these are all smaller. Unfair? Okay. All right. So ibuprofen's a molecule. You probably have used some at some point. I have. It's not a big deal. Sit around everywhere. It's just a molecule, though. Cocaine has cost many, many lives in many different ways, but it's still just a molecule. Right? It's a molecule, and it has a mass. So you put it in a mass spec, you'll see a mass, and it's 303. Not a lot of information. That is what it is. You can see some fragments. These fragments come from this molecule could break up into smaller pieces when it gets hit by high energy electrons. But the single most important thing is what's right here. You were looking for the farthest to the right on your mass spec, and that gives you the mass of the molecule. If we were to zoom in, you can see that you have a little peak at 304. That's due to the isotopes. And what is it telling you? You have some carbon 13. Is that okay? Sure. It's not very meaningful. All right. So the first thing, and probably the most important thing that you can tell from mass spec is the mass of the molecule. The second thing that you can tell from the mass spec is the presence or absence of a few specific elements. And those we're going to go through next. That's in the next 4 things. One of them is nitrogen, and then the other 3 are all halogens. So nitrogen and halogens. Through a really cool fluke of math, something we will see for most molecules is that their numbers will look like this one. So I'm going to scroll real quick, but don't worry about it. The first one, here's some molecules, ibuprofen. It weighs 206. All right. This game is, what do these numbers have in common? All right, we're going to skip those 2. This thing doesn't have any nitrogen. Its mass is 74. This thing doesn't have any nitrogen. Its mass is 120. This thing doesn't have any nitrogen. Its mass is 168. This thing doesn't have any nitrogen. Its mass is 102, but it looked like 84. What do all those numbers have in common? They're all even. Cocaine has nitrogen. Its mass is 303. This molecule has nitrogen. Its mass is 113. So give me a rule. If a molecule has nitrogen, its mass is odd. This has always been true. We've never talked about it. You probably never thought of it before, but the mass is odd. And so the molecular ion is going to be at an odd number. The reason for that is that carbon weighs 12, which is an even number. The number of hydrogens in your molecule is 2 times your number of carbons plus 2. 2 times any number is even, plus 2 is even. So carbons are even, your hydrogens will be even. If you add oxygens to your molecule, they don't add to your number of hydrogens at all. Oxygen weighs 16, so that's also even. Halogens always weigh an odd amount, but halogens always replace hydrogens because they make one bond. So an odd mass replacing an odd mass doesn't change your mass, so your mass remains even. So if your molecule is comprised of carbons and hydrogens and oxygens and halogens, your mass will be even. The only thing that will make an organic molecule have an odd mass that's neutral is a nitrogen. And the reason for that is not that nitrogen itself has an odd mass, because nitrogen weighs 14. But if nitrogen gets added into your molecule, let's just say somewhere along the chain, here we go, CH3, CH2, blah, blah, blah. All of that stuff with carbons would end up being even. But if you stuck a nitrogen somewhere in your molecule, nitrogen makes 3 bonds, so it'll bring an extra hydrogen, and it'll always make your number of hydrogens odd, which means that your molecule as a whole will have an odd mass. Whether or not you remember anything I said in the last 45 seconds, odd mass indicates a nitrogen. And if your mass is even, it indicates you don't have nitrogens. Technically, 2 nitrogens would make it even again, but we're not going to worry about that. Sound good? So that's it. Your mass is odd, you've got nitrogens. Technically an odd number of nitrogens. Ta-da. That's it. Remember that? All right. It's not a kind of thing, we don't usually look at numbers and say, haha, an odd number, but in this case, do that. By the way, we're not talking about the fragments. There are going to be odd and even fragments. We're talking specifically about the molecular ion. All right, let's look at chlorine, because chlorine and bromine both have some really cool isotope things. Bree, I keep calling on Caleb. Can you see the mass of chlorine from where you sit? So what's the mass of chlorine?
35.
So chlorine's mass is 35.45. I'm going to round that to 35.5. So once again, this non-whole number comes from the fact that chlorine is isotopes, or there are isotopes of chlorine that weigh different amounts. And it's not that half of chlorine weighs 35 and half of chlorine weighs 36. It's that 75% of your chlorine is chlorine 35, and 25% of chlorine naturally occurring is 37. So both of them are odd, but they're always going to give you a spacing of +2, because they're always going to be 2 apart. And furthermore, you're going to have a peak at 35, which is going to be the tallest because most of chlorine weighs 35. But you'll also have a significant peak for your chlorine 37s that's going to be a third the height because 25% is a third as much as 75%. So what this looks like in terms of a mass spec is no matter what else is in your molecule, you'll have a peak and then you'll have a peak 2 higher. Because most of the time your chlorine weighs 35, but sometimes a significant amount of time, your chlorine weighs 37, which is 2 more. So this is what it looks like when we zoom in a little bit. Here is our peak at 74. That is your molecular ion. It's the tallest peak in that kind of cluster or group off to the right. We have already said that our M+1, which would be this little thing right here, doesn't really matter. That just comes from us having some carbon isotopes, which we will always have, so we don't really worry about it. But in M+2, which is this thing right here, M+2 is just the mass plus 2, so this would be 76, 2 higher than your molecular ion. It's 2 higher than we, or it's much taller than we might expect. There's always a chance that you'll have an M+2 that comes from having 2 carbon 13s, but the chance of having 2 carbon 13s should be like 1% of 1%, which should be pretty low. So the indicator that you have a chlorine in your molecule is because of that effect of chlorine 35 shows up 75% of the time, and chlorine 37 shows up 25% of the time. So wherever this molecular ion peak is, if you have a peak at M+2 that's about the third of the height, it's telling you that you have some weird isotope thing going on. Specifically, you have chlorine in your molecule. And this is something that we didn't see in any of the previous ones. But what you're looking for is, it indicates the presence of chlorine with an M+2 peak. It's about 1/3 the height of your molecular ion. And so it looks like this. And that's because a third of your chlorine weighs 2 more than 35. And so you guys take a second and scan backwards, you'll see that you might have a little tiny M+2 peak in those other ones, but it's really, really tiny. We're not talking about the fragments, just your M+2 peak. So this is the first one where we've seen a pretty decent sized M+2 peak, and that tells you chlorine. So there's 4 of these little weird things. One of them is if the mass is odd, then it's telling you nitrogen. Second one is if you got an M+2 peak that's about a third the height, it's telling you that you've got chlorine there. Likewise, the absence of that is telling. None of those previous molecules had chlorine because they didn't have that M+2 peak. All right, questions on that? Okay. All right, Bree, how much does bromine weigh? 79.9. All right. So it's very simple. And when you guys did, figuring out stuff in Gen Chem and stoichiometry and all that, you probably just rounded it to 80 and said 80. But bromine never weighs 80. It weighs 79 half the time, half-ish, and 81 the other half. So much like chlorine, the mass of those isotopes differs by 2. But with chlorine, one was 75%, one was 25%. But with bromine, it's 50-50. So what you'll see is a peak and a peak that's 2 higher that are separated by 2, but they're about the same height because half the time it weighs 79, half the time it weighs 80. It's about 50% Br 79, and it's about 50% Br 81. So this is what we would see. Here's your cluster around the molecular ion, and you've got 2 peaks. And note that they're separated by 2. So the first one we would call our molecular ion, and the second one is 2 higher, so that's M+2. That is the indicator that you have bromine in your molecule. So the farthest to the left one is from bromine 79 being present. The farthest to the right one is from bromine 81 being present. And that's it. So when you're figuring out the mass of your molecule, you should start with 120 and remove 79. And what would that give you? Oh, math. You can do it. 120 minus 79 equals 41. Correct, 41. So the rest of the molecule weighs 41. All right, we're going to shake it up a little bit. What's 120 plus 2? 122. What's 122 minus 81? 41. It's also 41. So no matter which way you go, this molecule is 41 of something plus bromine. And if that plus bromine was 79, you'd get 120, which you'll get half of the time. And the other half of the time, the bromine would weigh 81. Your 41 plus 81 would give you 122. And that's why you see those things. Does that sound unfair? All right. So bromine is indicated in mass spec with, you're going to have an M plus and M+2 of the same height, approximately the same height. So when you find your molecular ion, if you got an M+2 that's the same height, that means you have bromine. If you got an M+2 that's a third the height, it means chlorine. And if you don't have an M+2 that really sticks out at all, it means you don't have either of those things. And if your molecular ion peak is odd, you have nitrogen. And if it's even, it doesn't have anything fancy, it probably doesn't have any of those things. Sound good? So these are little tiny bits of information, but they end up being really helpful. If you think back to IR from last week, one thing we didn't talk about was halogens. It doesn't tell you IR about the presence of alkyl halides. It does tell you about a bunch of functional groups that contain oxygen or nitrogen, but nothing about halogens. So IR and mass spec go really well hand in hand. They tell you different overall things, plus IR doesn't know anything about halogens. Well, mass spec does. So it's great. They're good friends. It's a good combination of spectroscopy. All right. There's no great trick for iodine, but there are some really clear indicators of iodine. Going back to essential outcome 4 from last semester, stability of ions, we may remember that as an atom gets larger within the same group or the same column, their subshells are farther and farther from the nucleus. And so having a +1 or a -1 charge from adding or removing an electron is less impactful on stability. In other words, it's not that big of a deal to have a big atom with a +1 or a -1. They're more stable with those charges. So an F+ is really unstable. A Cl+ is really unstable. A Br+ is pretty unstable. An I+ is actually pretty much fine. So when we fragment a molecule that has iodine, breaking off an I+ is something that will regularly happen. All right, what does iodine weigh? You can round it. 127. Right. So if I+ comes off all by itself, what'll it weigh? Don't think too hard. 127, exactly. So if you have a peak at 127, it could be I+. But there's a lot of ways of having fragments at 127. So there's kind of two things that go hand in hand for a molecule that has iodine. First off, you will consistently break off the iodine. So you will consistently have a peak at 127. Furthermore, if you have a pretty big molecule, I'm going to make a nice round number for you. You ready? If your molecule weighs 227, and you break off iodine, what's left? 227 minus 127 equals 100. Okay, the difference between 227 and 100 is very big. So iodine itself weighs a lot. And when you're looking at mass, the gap when you break iodine off would be big. It's 127, that big. So if you have iodine in your molecule, you'll see two things that show up hand in hand. One is you'll have a huge gap from the molecule down to a fragment. And secondly, you'll see a peak at 127. And that's what we're seeing right here. The molecule weighs 168. That's still the most important thing. But you see that you have this enormous gap in between your fragments. And the only one that's showing up is that little 127. So iodine doesn't have a fancy trick like bromine or chlorine or even nitrogen, but there is one way to pretty simply spot it. And it's that you will have a big gap and a 127 peak. Big gap in fragments and peak at 127. And that corresponds to I+. And pretty much the rest of this is what you get if you remove an iodine from it. All right, so that's our 4 elements that we need to be able to identify. So here's our big picture for the mass spec. Number 1 thing you can tell, mass of the molecule. Things 2 through 5, presence of nitrogen, chlorine, bromine, iodine. I'm good? All right. I will warn you on your quiz on Wednesday, there's going to be questions on IR and there's going to be questions on mass spec. How you feel about mass spec? Seems fine, right? Doesn't take too long to get the idea. How you feeling about IR? Yeah. All right, practice IR, please. And practice mass spec too. But like, I know that we spent 1 day on IR and 1 day on mass spec, but realistically, you're probably gonna have to put a lot more time into IR than mass spec. But get the mass spec questions right, it'll be great. All right. 2 more quick things for mass spec and then we're just gonna practice. You might remember on Friday, you might not, we had one major issue with IR, which was that if a bond was completely symmetrical, it didn't show up. So we saw that with an alkyne that was fully symmetrical, it just didn't show up. And basically an IR lied to you and said, there's no alkyne here. The same thing happens with alcohols in mass spec. So remember what we're doing is we're just randomly shooting molecules with electrons and we get what we get. And what we get is the most stable or this possible positive charges that come out. Turns out when you're shooting these alcohols, it's far more likely, far more being like 100% more likely, for you to remove the OH and a neighboring hydrogen than it is for you to split off an electron of a CH bond. So you're far more likely, because it gives you a much more stable product, to have an M-18 from removing water than you are to ever have the molecular ion show up. So that situation where you just remove an electron and you end up with the molecule with a plus charge, it almost never happens when you start with an alcohol because it's just so much more stable to kick off water. And so basically, if you started with an alcohol, mass spec will lie to you and tell you that your mass is 18 lower, which seems terrible, except when you remember that you almost always do IR and mass spec hand in hand. So do you remember, Olivia, what the peak looks like in an IR for an alcohol?
Just a parabola.
It's a pretty smooth and obvious parabola around like 3,300. So the great news is that if you run IR, it's very obvious whether you, it's not obvious that you remember it, but it's very obvious if you do remember it, that that's what there's an alcohol present. So those kind of this thing's Achilles heel goes hand in hand with one of the most obvious things of IR. So if you have an alcohol in a molecule, maybe remember, mass spec's gonna try to lie to me, okay? But I'm not gonna give you this molecule and expect you to tell me anything besides this thing weighs 84. If you looked at this this mass spec, you should say molecular ion is 84, right? Because in a bubble, this is lying to you. But if we can start to put some of those things together, then we can figure some things out. All right, so don't go looking for that issue, but I want you to be aware of it. If you have an alcohol, mass spec's gonna be incorrect most of the time. All right, so here's our last thing that we can do with mass spec. And this is nothing from looking at it. It's just something that you can do given a molecular ion and therefore a mass. If you have the mass of a molecule, you can propose a molecular formula. In taking a big step backwards, our goal with spectroscopy is to figure out what this unknown molecule is. And a molecular formula is really handy for that. Remember, very much the beginning of last semester, essential outcome 1. I gave you a molecular formula and said, draw a molecule. Make sure it was a Lewis dot structure with all the electrons in the right place. Remember that stuff? You did it and you could do it. And if I asked you to draw like a C5H8 right now, I bet you could do it. You'd groan, but you could do it. It'd be fine. That is, I never told you draw me something that weighs 101, but it's not a big step. So let me show you how you do this. You could do this. You can probably figure it out, but we'll work through it together. All right, City, 101. What does that tell you?
The molecular ion has a mass of 101.
Right, so the mass is 101. And is there anything in particular that this peak tells you is present in the molecule? It's one of those 4 things.
Nitrogen.
Yeah, someone yelled, but they didn't.
I didn't hear it.
I think you said nitrogen, right?
Yeah.
Nitrogen?
Yes.
How do we know it's nitrogen?
Odd.
Yeah, it's an odd number, all right? So this tells you that your mass is 101, so everything in the molecule weighs 101, and that you have nitrogen. So here's how you can figure out a molecular formula. Start at 101, start subtracting. You're going to take out a nitrogen because you know that there's one there, so that weighs 14. 101 minus 14 is correct, 87. Good job. I would like you to make the assumption, because you can't tell from this whether or not there's oxygen, make the assumption that everything else is carbon and hydrogen. You kind of play blackjack with your carbons. You start adding up carbons until you get close to that number without going over. Sound fair? All right, you can do it a little bit by trial and error. 1 carbon weighs 12. 2 carbons weighs 24. Blah, 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 blah. 5 carbons weighs 60. 6 carbons weighs 72. You can use a calculator if you need to. 7 carbons weighs 84. That's as close as I can get without going over 87. So if 6 carbons weighs 72 and 7 carbons weighs 84, which do you think is more likely for this? Either is possible.
72, because you still got to count the hydrogens, don't you?
Yeah, you still have to count some hydrogens. So 72 is reasonable, 84 is possible. Let's go ahead and just say we're actually getting as close as we can without going over. So 7 carbons would weigh 84, and that would give you 3. And so it's possible that your molecular formula would be C7, this would be 3 H's, H3N. I hope you're raising your eyebrows a little bit, because it's pretty hard to draw a molecule with a nitrogen and 7 carbons, but only 3 hydrogens. You could do it, you'd have a bunch of triple bonds, I guess. All right. So this is a possible molecular formula, but more likely, was that Miguel? I don't have it on my screen who's talking in Zoom, but.
Were you asking me?
Yeah, are you Miguel?
Yeah.
There you go. All right.
Last I checked.
6 carbons. So if we account for 6 carbons, that would subtract out 72. And 87 minus 72 is 15. And so it's possible that you could have 15 H's there. And so this is C6, H15. So those are both reasonable molecular formulas. I would say that this one is far more reasonable. If I asked you to draw a structure, you could do it. Ready? 1, 2, 3, 4, 5, 6, NH2. And this would have, as we go, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 hydrogens. We did it. And we drew a molecule. I don't know for sure that this is the molecule that gives you this, but it's a possibility. So I just made a guess at a molecule based on that one number and the fact that it's odd. And you could do that. So how do you feel about this little math thing right here? You can do that, right? Practice it. There's not a lot of tricks to it. You probably did it in Gen Chem a bunch of times. But you're just subtracting out until you get to a reasonable molecular. And those will be the things that I ask you to do about mass spec on a quiz. Tell me the mass, which is not, I'm not really going to ask you to tell me the mass because I know you guys can read. But what element could be present based on the fragmentation pattern or based on the isotopes, based on the things we talked about today, and decipher either a molecular formula or draw a possible structure. All feel doable? Great. All right. Any questions? I am going to. I pulled up some old quizzes from previous years, and we're going to spend the rest of today's class, 10 minutes, just going through some examples. So here is, you didn't print these out, so here we go. Let's start with IR. This is what, all right, so if this was your IR, there's a whole lot of peaks. I do not expect you to be able to look at that and tell me where those peaks are. So instead, what I will do is what you could do if you had the actual instrument spinning sitting in front of you. I will tell you exactly where all those peaks are, right? Number-wise. Because, I mean, you could roughly guess, but guessing is silly when practically you would just be able to zoom in. So what I recommend you do when interpreting an IR is to start with the fingerprint region, right here at 1500, cross it all out. Because the fingerprint region is something that we use when we have something to compare it to. If you don't have a database in your brain, cross it all out and ignore it. And then start from there and work your way left. So here is a peak at 1603. Here is a peak at 1700. Here's some peaks, and we'll get to those in a minute. All right, one thing we didn't talk about on Friday is what happens if you have a peak around 1600. So I wanted that to be in our first example today. All right. So without looking at your notes, or with looking at your notes, does anybody remember what shows up at 1600? It's a total trick because there's nothing. Do you remember what shows up at 1650? Alkenes show up at 1650. An amide does because an amide is a C double bond O with resonance. Resonance pulls peaks down by 50. Resonance is only really possible for double bonds. So this only really doesn't happen for every peak. It just really happens for double bonds. So a carbonyl, a C double bond O, Kylie, where does a carbonyl show up? It was for ketones or aldehydes or any of that stuff. 17 something? 1710? Great, right. 1710 is where we would expect a carbonyl to show. But an amide shows up 50 less, around 1660-ish, because of resonance. Where does an alkene show up? Cindy just said 1650. But what happens if an alkene has resonance? It'd be 50 lower, which would be 1600. Yes. So the one peak that we didn't specifically talk about on Friday was that an alkene shows up at 1650. We did. But if an alkene has resonance, it would show up 50 lower, which would be 1600. So you can put that in your notes from Friday, or you can write it down now. But this thing right here, a 1603, is an alkene with resonance, which would be 1650 minus 50, or 1600-ish. Most likely, an alkene with resonance is a benzene ring, which looks like this. So probably benzene, but not necessarily. So that's an alkene with resonance. So that would be one to know. It's one to remember. All right, next we have this one at 1700. 1700 is really close to 1710. So Bree, what was 1710? Ketones or? There's those other carbonyl containing ones. So ketones or aldehydes or? Yeah, the carboxylic acid. Yeah, carboxylic acid. All right, so part of the reason that I suggest you go from right and work your way left is that you'll run into that carbonyl first. And when you run into the carbonyl first, I want you to say to yourself, okay, I have one of those carbonyl containing functional groups. If it's right around 1700, it's one of three possible things: ketone, aldehyde, or carboxylic acid. If you have a carboxylic acid, then you have the 1710 plus you have the carboxylic acid's OH. That carboxylic acid's OH, you remember what that looked like?
Messy.
Yeah, it was a big messy thing that went from 2500 to 3500 and overlapped everything. You have that in this spectrum right here. No. So it's not a carboxylic acid. So it's a little process of elimination. If you had an aldehyde, then you had that 1710 plus aldehyde had that H, which showed up as those twin peaks around 2700 and 2800. Do you have any, by looking at this, it's hard to tell, but I gave you numbers. Do you have any numbers around like 2720? Don't think too hard. Is there a number there around 2720? No, there's not. So that means it's not an aldehyde. So if you have 1710, so you have a carbonyl, look for, is it a carbonyl and a carboxylic acid? In this case, no. Is it a carbonyl and an aldehyde? In this case, no. So then by process of elimination, it must just be a ketone. So this molecule has a ketone. Sound good? All right, I do have some stuff over here. All of these peaks, 2800 up to 3000, that's this big blob right here. What does that tell you? I asked this question many times on Friday. You have some alkane. If I'm asked, the question here is identify any and all functional groups. Feel free to not worry about writing the word alkane. You can if you want to. Yes, there's alkane. There's always alkane. Cool. Alkane. All right. And then the only other peaks here, we kind of went through and did all of these, are those 3031, 3060, and 3086. Those are the ones in between 3000 and 3100. So all of these are CHs. These are the CHs of alkanes. What were these the CHs of? It's not alkane, but it's close. Alkenes, yes. So these are telling you that you have an alkene. Is that new information to you? No, you already told me there was an alkene with resonance. So the fact that you still have an alkene doesn't really tell you anything else. So what functional groups are present in this molecule? I'll give you a hint. They're written in front of you. Ketone and alkene with resonance. That's it. So there are a lot of peaks labeled here. There are 9 different peaks labeled, but so I wouldn't be completely just follow and try to label every single one of these, but start over here and work your way to the left. Start over here, work your way to the left. What you'll find is the stuff on the left most of the time doesn't bring you anything brand new, or at least a lot of times it doesn't. So you can just kind of hand wave all of these things and say, oh, those are just alkane. And oh, those are alkene, but I already knew that. So it's not new information. That's it. I did one for you. All right. Let's do another one. I'll let you guys do this one. All right, good news, Savannah. This one's easier. It's a multiple choice question. So this IR right here corresponds to which of these molecules? Let's walk through and do it. So tell me what we should do first. All right, so we're going to cross that off. It always feels good to cross off a whole bunch of peaks. All right, and so let's start right here. What is this thing? 1656. Alkene, right. Does it have resonance? Nope. So remember that if you got something around 1650, it's either an alkene without resonance or a carbonyl that had resonance, like an amide, or even like a ketone that's got resonance. But a carbonyl, like this one right here, a carbonyl is a super strong peak. It'll almost always be the strongest peak on your spectrum. And so this is definitely not a super strong peak, so that's definitely an alkene. So good job. All right, let's keep going. What about all of these things right here? Which is all these guys. Yeah, you get to do this whole one. You're welcome. It's because you're my favorite student. Don't tell anyone. All right, so all these 2,800 to 3,000 peaks are, yeah, okay. So congratulations, you got it. Okay. All right, what about this stuff around like 3,000 to 3,100? It is. So that's not new. All right, what about this is new right here, this thing? Yeah, great. So what do you have in this molecule? Yep. So here you go. A, B, C, D. Which one's your molecule? I'll give you a hint. It has an alkene and an alcohol. It's a double bond, C double bond C. It is. All right. Fun side note, review what the names of those functional groups mean when it comes to the molecule. Okay. All right, how are you feeling about this? Cindy, just so you know, everyone's my favorite student. I will tell everybody that. It's true. Okay. I know it's your first day. You're already my favorite student. Don't tell Olivia. She thinks it's just her. So going through these, I know we're out of time. You looked at this one, 76, you see that n plus 2 1/3 the height. You would say to yourself, chlorine. This one has a mass of 93. You would say to yourself, nitrogen. And then the last question, draw a reasonable structure for one of those mass specs. So start with that number, subtract things out, get a molecular formula. I'll either ask you for a molecular formula or to draw a possible structure, and you could do that. Study, but you can do this, right? 2 bite-sized chunks, IR, mass spec. Thanks, I'll see you in lab or in class sometime. Have a lovely day. Anybody in Zoom have any questions? Thank you for coming today. I appreciate all of you.